Good morning, Sanatan.
Hi everyone. We'll start in just a minute.
No audio.
Sanatan, many thanks for your email.
You're welcome.
Sanatan, I have one question related to our field.
Yeah, go on.
Yesterday, I read a news somewhere that OpenAI is filing for bankruptcy in December 23.
I have no knowledge about it. Okay. So,
So, what does that have? I mean, what is going to be the compounding or the cascade?
it's not a data science company. So, I mean, was it related to data science since you mentioned it's about our domain?
Yeah, but like they are using the same technology right, to develop their tool or their chatbot.
No, I don't think many people use that tool for data science. Do you?
No. The
Okay.
what you call the science or the ideas they are trying to implement is through the technologies that we are learning today.
No.
So is chatbot built totally on Java? Is that
Yeah.
what?
Okay. Just a sec. Okay. OpenAI is a company which was built on transformers. They didn't build transformers. Okay.
They just inherited? Okay.
They made use of it because they had plenty of what we say backup from investors. So they had a lot of money. So they put a lot of money in hardware and they used an existing architecture, trained a model, and they figured out that, okay, there are certain things that this particular model can do, which would be effective. But probably if they are filed for bankruptcy, which means that the time probably has come to an end, or maybe they will have to shell out some more stocks to get more money, to get more investors coming in. So it's not related. So what essentially this means is they are unable to pay their employees.
Yeah, they are not able to get return on investment.
Correct. So I mean, you must have heard that, okay, Microsoft kind of invested $1 billion. I believe other companies also invested quite a lot. When you say return on investment, because they have not been able to entice other companies to integrate their products with them. So that is why probably they are suffering. See, the money will end after a while, right? And I don't think, or I rather say that all the time that 99% of the ideas fail. I haven't heard of a single a bright idea succeed. Can you name one over the last 20 years? There is only one, by the way. There's only one, by the way.
I think WhatsApp.
WhatsApp was not an idea. Okay, it was already there. Okay,
It's what you call rebooted or
yeah, I mean it's a form of a messenger with just better features. Okay, better scalability. So, I mean, do you remember when Facebook came out? And that was the one I was referring to.
okay.
And that is also going to die down soon. So, like the time has passed actually.
Yeah, in this day and age of video calling, phone requires all that.
Yeah. See, it's going to stay for a while. I mean, the new generation will find it difficult to probably leave those platforms. But once they realize that it's kind of futile, I mean, you don't get much out of it. So that is where I believe. I mean, once that happens, the usage is going to drop significantly. But it's not related to data science as such. I mean, you can say the failure of OpenAI.
Okay.
But what you hear, like in the news, okay, it's mostly fake.
No, this is on a business channel, what I have heard.
No, but for which business channel?
CNBC.
The news only, right?
Okay.
No, but
News as in sense business news. Yeah, correct.
but did the CEO came out and made the statement publicly, or was it just speculations? Unless he comes out and speaks, right? Okay, we can't trust such news. Okay, anyways, maybe this is for some other time. Yeah, all right. So today we are going to see one topic called as decision trees. Now, before I start this, if you guys have any questions related to what we have discussed in the past, please feel free to ask. Any questions?
No.
Okay. All right. So let's start with what decision trees can do. So the idea is frankly very, very simple. So you can use this idea. I mean, I'll describe the idea in just a while. So you can use this idea for both classification and regression. Okay, and when I'm talking about classification, it can directly work with multi-class data sets. So it's a multi-class classifier. So you really don't have to worry about applying the extension strategies. Okay, and the way it works, it doesn't treat features what we say dependently. Okay, so the features are kind of independent. So there is no need of feature scaling also. So we'll talk about that. Okay, why is this algorithm? Okay, I mean, why is there no need for feature scaling in this algorithm and other things in more detail? Okay, so let's start with a small example just to illustrate something. So I'm going to start with, so which example would you prefer? Can you take, say, a binary classification example? And I believe after that, it will be pretty clear.
Yeah.
Or shall I take a multi-class example? What do you suggest?
Binary.
Okay, let's start with binary. The extension is pretty straightforward, by the way. Imagine there are two features, say age and height. Okay, and we are trying to determine if the person is, say, obese or not, or let's say diabetic or not. Anything that you want. Okay, since we are saying it's binary. So there are some samples given to you, maybe like this. Some triangles here, maybe some x's here. Okay. Instead of making one here, maybe I'll make it here. Maybe some triangles here. Okay. Some x's here. Okay. Okay. So I believe this is sufficient just to demonstrate something. Okay. So if I give you this data set, as you can see, it's binary classification, right? There are two classes, triangles and x's. You can assume any one class to be, say, obese and the other class to be healthy. Now I have a simple question. Do you think a simple linear function is able to, will be able to separate this data? Any line that you draw, will it be able to separate this data perfectly?
No.
No, right? Doesn't make sense, right? Okay. So what we will do is we will try to draw multiple lines. Okay. And the lines that I'm going to draw, you can call them as axis parallel lines. Okay, let's see. See what I mean by axis parallel is, so let's say if I draw a line like this, can I say this is parallel to x2?
Yeah.
All right. So it does a separation, right? It creates two partitions. Can you see that? One on the right and one on the left. Does it make sense? So one line that you draw creates two partitions, right? Okay. So I'm going to make a structure. Please listen to this very carefully. So imagine I have all my data set in this node right now. Okay, this is the circle. So I'm going to write something in this circle. See to this very carefully. How many values that I have right now, which are belonging to class X? 10, right? And how many values? So 7 triangles are there. Okay. So this is my data right now. Now assume that you're going to use all your data to make a decision. Okay. So assume that you're going to make use of all of your data to make a decision. What would you finally predict? X, right? Because X is the majority. Spot on. Okay. Now the next idea is, see, we have this data and you can see it's a two-dimensional space, right? I'm going to partition this space into now two parts. So one of the ideas that I can use is, let me draw an axis parallel line. So you can draw a line like this, you can draw a line like this. So anywhere, wherever you want. Okay. But the line has to be parallel to, so it's a line that you're going to draw. So it would be horizontal, vertical, because we are in 2D. Yeah, we are in 2D. Okay. So let's draw a line, okay, somewhere, and then we will talk about why did I draw this line. Okay. So I'm going to draw a line maybe like this. So if the value of this is, let's say, B, okay, just a constant B. So can I say that if I use the threshold as B, can I say that anything which is greater than B will fall in the right-hand side? Yes or no? Does that make sense?
Yes.
And greater than B will mean this partition. So you just saw that I broke my data into two partitions. Okay. So if you look at the top partition, which is having the values of X2 as greater than B, that will have 2 X's and 7 triangles. Does that make sense?
Yeah.
Okay. And anything which is smaller than this is going to be, say, all the triangle or all the X's, which is around 8 X's. Okay. Now I have a question. So let's say we have done this partitioning. Okay, just a second. Okay. Okay. So this is so 2 X's and 7 triangles. And this is 8 X's. Okay. Now my next question is this. Let's say if I give you a sample, okay, if I give you a sample, the sample values, so I'm going to give you a two-dimensional sample for making a prediction, right? It will have two values, X1 and X2. And then your job would be to determine whether it is belonging to class X or class triangle. So I'm giving you this value, let's say, so assume this B is, say, 10. Okay. This B, you can assume it to be 10. Okay. So let's say this is 15 and say this is, say, 8. So 8, 15 would probably lie somewhere here. This is the test point. My question is this. What would you predict it as now? So if you pass this to this structure that I'm making, where would you go? To the left or the right?
Right.
To the right.
The right, okay, because the value of X2 is greater than 10, right? So you go right, and what is the majority on this right?
Triangle.
Triangle, right? So, and you see that, okay, it is closer to a triangle, right? So I hope you have realized by now, what I'm going to do is I'm going to partition my data in such a way such that each partition becomes pure and pure. When I say pure, the samples belonging to each partition should be of the same class. Okay, let me show you one more time. Okay, so do you think, is there a need to split this partition?
No.
Right, because everything is an X. So there is no confusion here, right? If I give you a point, which is say 8, 7, what do you think you will call it as?
The left side.
It is X, right? And
Yeah.
there is no triangle here. There is no confusion. Okay. There is no confusion at all. You are very, very sure that it's an X. So there is no need to split this, right? I hope you understand that. Okay. So the partition, when you don't have to, okay, what is the criteria for you not to split it? Think about it in plain English words.
When I have reached a point that there is only one class in that partition, then there is no need to
No,
partition.
no need to split it, right? Keep that in mind. We'll use this idea. We'll effectively have different ways to measure it. Okay. So I'm going to encircle it. I mean, you can say make concentric circles or concentric ellipses just to demonstrate this will not be split. Okay. Now, is there a need to split this further? The right hand side?
Yes.
I can, right? And,
Santan, sorry to stop you. So, you said we have the test point of 8 and 15, and if that point goes up there, then we'll predict it as a triangle, right?
correct.
Excuse me.
Yeah.
But if we were predicting as because of there is a lots of triangles, so that our machine will automatically predict this at a triangle, right? But
Yes.
okay,
So I'm asking you, what's the question?
like I was about to ask it, but 1 minute.
There has to be a question somewhere, right?
1 minute. Yeah, you said then the output will be pure, right? But however, there is a 2x's. You don't.
Pure? No. I never said the output will be pure. What is it that you're trying to imply here with this statement?
Like I was about to ask it, but suddenly, I was.
It's okay. It's okay. Let's see the subsequent steps, and probably you'll have the question right now.
Okay.
It can happen. So, all right. Now my question is this: if this is the right-hand side partition, if you see this, I should be splitting it, right? Because this is not pure. In this partition, you have some x's also. So my next question is this: where do you think I should partition it? I mean, using x2 or x1?
Another x2 value or line
X2.
parallel to horizontal axis.
That makes sense, right? To everyone. I should not use x1 because if I do that, it will not help. So you had some intuition in your head, right? That x2 should be used and not x1. So you just selected a feature to split your data, like the way I did it, like this.
Yes.
Okay. And what was the criterion in your head? Can you describe it in simple words?
A split that can actually like give me an ambiguous result that
Spot on. The split, you should use that particular feature to split your data, which leads to more pure partitions, right? The purity level in the children, the new partitions should be more pure, right? Does that make sense?
Yes.
Okay, that is what I want, right? And it makes sense to use x2, not x1, because wherever I draw a line on x1, that will not create pure splits, right? Wherever you draw it. Yes or no? So it makes sense to use it on x2. So let's use this one point, this x2. Okay, let's say this is say 12 maybe. And you say, okay, x2 is greater than 12. And then on the right hand side, you have 2 x's. On the left hand
x's.
side, you have 7.
Triangle.
Okay. Now look at the same thing. Okay, the point that I gave you earlier. What would you finally predict?
x.
Okay. So do you realize that? Okay. As I'm going down the tree, I mean, I shouldn't call it a tree as of now because I haven't explained what a tree is. If you look at this structure, if I go down the structure, I'm creating small and small partitions. Yes or no?
Yes.
And if I create small and small partitions, okay, in the worst case, how many samples would belong to each partition? In the worst case.
First case, equal number of samples.
In what respect? Now, when
Equal,
no, I'm saying in the worst case, let's say you are creating more and more partitions as you go down this structure that I'm creating. Don't visualize this as the data which I've given to you right now. But what can happen is, like as you create the structure, right? As we go down, do you realize that okay, after each step, how many new partitions get generated? Okay, originally, how many partitions are there at this level?
One,
One.
yeah.
Everything is only one. So as you split it, how many partitions were created?
2.
So do you realize that one new partition was, I mean, basically, you just split this original data into 2 partitions. So now you
Yes.
have partitions of your data. At this stage, you created one more, but how many total number of partitions are there? 3 now.
Yeah.
So can I say that at every step, when I'm splitting, I'm creating one new partition? Basically, I should say that the number of partitions increased by 1. Does that make sense?
Yes.
At each step, the number of partitions increased by 1. Okay. My question is this. So as you go down the structure, your partitions will increase by 1, right? Okay. How many maximum number of partitions are possible? Think about it. In the worst case, how many? So currently I have 3 partitions, as you can see. In the worst case, how many partitions will you make for any given data set? See, a partition needs to have one sample at least. You cannot say a blank partition is a partition. So how many partitions will be created in the worst case? Equal to the number of samples.
Yeah.
Every sample will fall into one partition, right? And what is that scenario called? When you give importance to every freaking point to learn, okay, to learn what happens.
Overfitting will happen.
So do you realize this kind of technique is more prone to overfitting?
Yeah.
Okay, let's try to describe, okay, what will happen, okay? Now think of this. See, overfitting means that you are doing excellent on the train set, right? Are you convinced with this statement?
Yeah.
Okay. Now, I'm going to show you that you'll be 100% accurate with the structure that you created just now. Okay, let's see this. Pass this point. So this point will have some value for x1 and x2, right?
Mm-hmm.
What will be the x2 value for it? Will it be higher than 12 or smaller than 12?
Higher than 12.
Okay, so let's see this. Okay, you are going to pass this point and let's see what it predicts. So if this is higher than 12, where should I go? To the left or the right?
Higher than 12. To the right of the second line.
Okay, again, your value is higher than 12. Where should I go?
To the right.
So what do you predict?
Oh, there is a axis only, so I'll predict
It
X.
was E and X and got predicted as an X. Can I say
Yeah.
this sample got correctly classified? Do you realize that you ended up in the same partition
Yeah.
where it was belonging to? So if I pass any of these points again, what do you think they will be predicted as?
X.
I mean, I'm saying all of these points, if I pass them again one by one, what do you think they'll be predicted as? Their actual label. Yes or no? Think about it. So, okay, think about this. Okay, let's say if I do it for this point, what do you think it will be predicted as? Okay, what is the value of x2 right now? Between 10 and 12, right?
Yeah.
Okay, so you will go to the right and then you will take a left because it is not higher than 12, right? So do you realize that this triangle is coming from this middle partition, right? And we are ending in that same partition, which is this 7 triangles partition. Yes or no?
Yes.
So if I pass any of these points back again, can I say all these points will be correctly predicted? If you have understood this, say a yes.
Yes.
So what would be my training accuracy?
100%.
100%, right?
Yeah.
All points would be correctly classified. So if you make such a structure, your training accuracy comes down to 100%. Don't you think that you are more prone to overfitting?
Yes.
Okay. And how can you overcome this overfitting? Like just by the basic understanding
Adding
in
a,
this by
adding a penalty.
no, here how would you add a penalty? Think about this. Try to interpret what would be the penalty for this. Try to see what would be a penalty for this. Okay, let me ask you this. So let's say if I would have stopped the tree here at this level, do you think all your points should be correctly classified?
No, where do you say?
At
First,
this
second,
point.
first.
At this point.
No, like then the triangles.
Then the X would be identified as triangles.
Yeah.
Yes or no? These two X's would be identified as triangles. Yes or no? So do you realize that maybe because there is a lot of majority in the triangles over there, in the test points, it might be beneficial? Yes or no? See, you are looking at the train data right now. Okay. Test data is unseen. Can I say that there is a chance that if I give you any point here, it might actually be a triangle and not an X? Yes or no?
Yes.
But if you went down, you actually predicted it as an X, right?
Yes.
Yes.
Okay. So can I say that to avoid overfitting in this, I should reduce the size of this? I mean, I should not go deeper. Yes or no?
Reduce the size of a tree or
See, as I grow the structure, do you see that this will tend to overfit?
yeah.
So I'm saying that if I limit the size of the structure, can I say that I will avoid overfitting?
Yes.
That is the idea. This is the penalty that you are having. Okay. So we'll discuss these things in detail. So let's talk about why this is called as a decision tree. Okay.
Sandon, like you said, we gonna cut it with that 8x, like the one classification, right?
Let's wait for that. It will be covered after 1 hour. I just wanted to give you an intuition that reducing the size of the structure will lead to, you can say, a penalty on the training set. Yes or no?
Yes. But
So, yes, go on.
yeah, like the point.
Have to check on the test set whether it benefits or not. What's the question? Okay, phrase your question properly.
Yeah. So the point you said, right? Like the point with the arrow mark. So if I'm going with a point, however, like the point is about 12, right? So that it's going to be predicted as X, right? So you said
If you had created this full structure, then it would be an X.
so if not, it will be predicted as triangle. So that
So
okay. So that the overfitting. Okay, fine.
no, I am saying that no, that is not. See, again, you connect several dots. Huh? I don't know how.
No, that then it will be predicted as triangle, so that the overfitting will be avoided, right? So that
No, again, overfitting is with respect to the train set. You are trying to connect it with the test set now. I don't know why. The point that I raised earlier, if you look at any of the points in the train set, okay, if you look at the full structure, each point would be identified correctly, yes or no?
yes,
The full structure, and then you pass a point, you will see that this any point will end in its respective partition. And since all the partitions are pure, they will be predicted correctly. Does that make sense?
yeah,
So what is the accuracy of this training set? 100%.
yes,
Is a training accuracy of 100% always going to give you 100% test results also?
no,
Not guaranteed, right? And so
Yeah.
what is this phenomenon called? Overfitting.
overfitting.
See, I'm saying that if your training performance is so excellent, okay, maybe it is not excellent on the test sets on unknown data. So if it is not excellent on unknown data, I can check, right? Once I create this tree, I can check if the results on the test set are good or bad. Assume
Yes.
they came out to be bad, then I can call it as overfitting.
We can.
Okay.
Yeah.
But let's say if I stop my structure at this level, okay, you have seen, okay, I have drawn these multiple
Yeah.
horizontal lines. So if I stop my, you can say decisions at this level, do you think that I might get an improvement in my test set? I might. I'm not saying always. It depends on what the test set is, right? I can
Yes.
check for the test set
Okay.
and compare my results. if it gave me an improvement, don't you think I just avoided overfitting?
Yes.
Because my performance on the test set improved actually. But now if you look at the structure and pass the training sets point back again, you will see that training accuracy reduced by for two samples. Two samples got identified incorrectly. These X's will be
Will be
identified.
identified as triangles.
Okay. So the idea is we have to limit the size of the structure, okay, to avoid overfitting. But we have to check. We cannot say always, okay, this will end up in overfitting. Okay. It is prone to overfitting. You have to check. Okay. You have to check. All right. We will discuss this at the end, not now. But this will demonstrate as you go down the structure, it tends to overfit. The performance of the train set improves and improves and improves. And when you have created all the partitions, pure partitions, right? It is 100%. And that is a bad thing to end up in because it might end up in overfitting. Okay. All right. So let's discuss about some of the things, some terminologies. So this is the type of structure which I made. Okay. I'm just making a small generic structure. So if I am stopping at particular node, I'm going to put concentric circles around it. So where the process ends, I'm going to put a structure around it. Okay. So first of all, this is called as a tree structure. A tree structure is one where there are no cycles. So do you think that if these edges are say directed, do you think you can come back to the same node by traversing this kind of graph? If you start from any place, do you think you can get back to the same node again?
No.
No, right? So a graph so in computer science, there is this branch of mathematics which is called as discrete mathematical structures. And therein you see graphs. Graphs are nothing but a collection of nodes and edges. Okay, these circles that you see, they are nodes. And the lines that I have drawn to connect them, they are called as edges. So if you cannot come back to the same node, if from wherever you started, so let's say you are going to take you can say a path, okay? You are going to walk, and if you cannot get back to the same node again, if you came back to the same node again, it is called as a cycle. But there is no cycle present in this graph, right? Yes or no? Does that make sense? You can only go down, right? You cannot come back up. There is no way. Okay. So a graph with no cycles is called as a tree. Okay. So a generic name for a graph which doesn't have any cycles is called as a tree. Okay. Also, can I say that okay. So you understood hopefully that why it is called as a tree. Okay. Why in the name you have a tree? Then I'll talk about why is there decision also there in a moment. Okay. All right. Now, this structure is called as a tree, but there are some terminologies associated with it. So this top node is called as the root node or the start node. This is where the process starts. This is called the root of the start node. The process, when it ends, you can see that I have drawn concentric circles around it. These are called as leaf nodes or terminal nodes. You can call them as leaves also, leaves of a tree. Like you can imagine like a real tree, and after the leaves, there is nothing, right? So leaves are the endpoints. Okay. All right. Okay. The nodes where you actually split the data. At what nodes do you split the data? Okay, I'm going to highlight some of them. This is one node. This is one node. This is one node. This is one node, and this is one node, right? The nodes, can you see that I've, kind of encapsulated them in rectangles.
Yeah.
These are the nodes where you will have some decisions to go to the left or the right. Yes or no? Okay.
Yes.
These are called as decision nodes, and that is why it is called as a decision tree. Okay. We are making decisions to end up in a partition. Can I say that each terminal node is a partition? wherever you end up, right? If you look at any node is a partition essentially. Okay.
Yes.
But where the process ends, you end up in a pure partition. All the samples are at the same time. Okay. Now, the nodes at which you make a decision. Okay. So one of them is the root node where you make a decision. Any node which is not a root node, but you are making a decision is called as an internal node or an intermediary node. So these are the nodes where you make a decision. Okay. You don't make a decision at terminal nodes because you're not splitting them further. Okay. I'm going to label some of them. Let's say this is A, this is A, this is B, this is C. Can I say that A is the parent of B and C? A is the parent partition, right? From which B and C are created. B and C are called as siblings. Okay, and let's say if there was this D, you can call D to be the grandparent. I'll use these terminologies as I describe them, as I describe the process later on. Okay. All right. There's one more thing that you need to know. So if you start from root, okay, and then you end up in a leaf node, this is called as a path. So from root to leaf is called as a path. Can you tell me how many unique paths are possible? Every path is actually unique, by the way. So how many paths are there in this? In the data, the tree that I have made, and the decision tree that I have made, how many paths are there? Equal to the number of leaf nodes, right? Every leaf node will give you one path only. Do you think that you can reach up to a leaf node in many different ways?
No.
There is only one unique path, okay, for every leaf node. So number of paths are equal to the number of leaf nodes. Okay, keep that in mind. All right. Okay. In the worst scenario, how many leaf nodes will you have? These are the questions they will ask you in the interviews. In the worst scenario, how many leaf nodes will you have?
Number of samples.
Number of samples. It is like a partition, right? So the worst case is one sample in each partition. Okay. All right. Okay. Now I'm going to ask you a few other questions just to understand, just to make you understand decision tree better. Now, see, I started my journey with this X2 axis at this point 10. This is where I started, right? Do you think that I would have made a structure by starting from X1? Yes or no? I could have made a similar structure, but I would have started from X1 like this. And I would have made then lines from X1 and X2 respectively, and would have obtained another structure which would also be perfect. Yes or no? It would more or less partitions depending on how am I creating them. Okay. So the first question is, I think we have discussed it in one perspective already. How to decide which feature to use? What was the criterion? We came up to a conclusion, right?
Yes.
So what was the criterion for that? How to decide which feature to use? I made a generic statement about it.
Divides my data into like two partitions.
Options, right? It gives more purity in the children. Okay. So you can say that B and C are siblings, or you can also say that B and C are children of A. Okay. So I want to select that particular feature, which gives me more purity. Okay. So I'm going to describe how to measure this purity first. Okay. So the purpose is this. I am given a data set, say, with multiple features. Okay. In the data set, I have multiple features, right? I have these outputs Y. Okay. So I have a data set given to me. I'm going to make this structure. Okay, I'm going to make this structure. Okay, assume that I have, say, two classes, maybe say 20 samples, 10 X's and say 10 triangles. Okay, just imagine this number. So currently I have 10 X's and 10 triangles. So I want to know how pure this partition is. My question is this: if all of them were X's, if all the 20 samples were X's, do you think is there a need to split it?
No.
No, right? Because then the majority would be X, right? I mean, not majority, I mean, it's a pure partition. There is no need to split it. There is no need to even discriminate because everybody is an X. Okay. All right. But currently, as you can see, I have 10 X's and 10 triangles. So let us try to measure, okay, how pure this is. Okay. So there are many ways to do it. I'm going to talk about the simplest way first, and then we will discuss more ways once I complete the process. Okay. So I want you to focus on this. So imagine there is a bag, and this has n number of X's, n number of triangles. Okay. I want to talk about purity. Okay. I put my hand in the bag and take out one sample. Okay, I take out one sample. Can you tell me what should be the values of m and n such that whichever sample I take out, I am very sure about it? What should be the value of m and n such that whichever sample I take out, I am 100% certain that whichever sample I take out is going to belong to a particular class? What should be the value of m and n in that case?
One should be either of one.
One should be 0, right? So can I say that it tells you the notion of purity?
Yes.
If one of them is, if one, you can say if either m or n is 0, can I say that I have purity? I mean, I have pure partitions? Yes or no? If either of m or n is 0, I have pure partitions. Okay. Now, in information theory, so decision tree originally came from information theory domain. In information theory, the concept of purity is measured through uncertainty. In information theory, the concept is measured in uncertainty. It's the same idea of purity. The idea is if I put my hand in the bag, I take out something, then how much certain I am that this is belonging to one particular sample. So they both are equivalent. They are contrapositive of each other. Purity is directly proportional to certainty. Okay. So there is one measure which is very popular, which can tell you how pure or impure, how certain or uncertain you are with a given, you can say, bag, or with a given partition. And the measure that is used is Shannon's entropy. What Shannon's entropy says, okay, I'll tell you the formula and then we will see, okay, how it is measuring it. It's a measure of uncertainty, by the way. So the more it is, more uncertain you will be, less impure it would be. Okay, the more it is, less impure you would be. Okay. So it's direct, it's, you can say, inversely proportional to purity. All right. Now there are many other ways to measure it. I'm talking about Shannon's entropy first. Okay, let's see this. So in what case you would be the most uncertain, or it would be the, you can say, most impure?
Both are equal.
Both are equal. And okay. So if both are equal, what is the probability of X in that case?
0.5.
0.5, right? Okay, I can write it like this. Similarly, okay. All right, because m is equal to n. Okay, keep that in mind. M is equal to n. Okay. Now, when okay, let me show you how Shannon's entropy measures it. The formula for Shannon's entropy is this: minus of summation I 1 to this capital C, this is the number of classes. The formula is pi log pi. The base is 2. Okay. Pi is the probability of a class. Okay. So for the given case, how many probabilities will I measure? How many classes are there?
2.
For this example, how many classes are there? X and triangles, right? So can I say that this formula is equivalent to writing minus of probability of triangle, log of probability of triangle, minus probability of X, log of probability of X. Any doubts about it? Okay, all right. Let's try to think of the, you can say the pure case, okay? When the partitions are pure, okay? So when the partitions are pure, can you tell me which value do you want to be 0? M or N?
M to be 0.
Okay, let's say M is 0. So what is the probability of X in that case?
0 is probability.
0. And let's say N is any value which is greater than 0. So probability of triangle is 1. Does that make sense? Okay. Put it in this formula. Minus 1 log to 1 minus 0 log to 0. See, 0 multiplied with anything, you can just remove it even if it is multiplied with infinite. Okay. What is log 1, by the way? What is log 1? Log of a number, log of 1 is any base. What is log 1?
0.
0. See, how you can interpret it is like this. Okay, can somebody tell me, let's say if the base is A and you are doing like this, okay, B to the power C. Okay, how can I write this? I can write this as this, right? C into log of base A and B. Yes or no? The power comes out, right? Does that make sense or not?
Yes.
You know about logarithms, right? Okay. Let's look at this. I am going to make, so my base is 2. Okay. I want to compute this log base 2 of 1. Okay. Can I write this 1 as 2 to the power 0?
Yes.
And then if 0 comes out, what is this? Yes.
1.
Okay. So any 1 can be written as the base to the power 0, right? Yes or no?
Yes.
That is why log of any base, which is any base it would be. If you are computing log of 1, it will come out as 0. Okay. All right. So this is equal to 0. Do you see that there is no uncertainty? See, Shannon's measure is a measure of uncertainty. So can I say that there is no uncertainty because you are all pure?
Yes.
Yes or no? Okay. And now let's see the case where you have the highest uncertainty. So where M is equal to N and the probability of X is equal to probability of triangle, which is equal to half. Okay. Let's compute Shannon's entropy for this. Minus half log half minus half log half. Okay. So I can simply write this as minus of log half. Base is 2. Okay. Don't forget that. And then I can write it as, so minus 1 comes out. What is log A of A? If the base is A, the value is A, what is this?
1.
1. So what is log 2 to?
1.
1. Okay, so do you see that you have the highest entropy right now?
Yes.
Okay, it is highest, right? Any value if you compute, okay, when M and N are kind of unequal, you will see that the value would be between 0 to 1. Okay. Now I have to make a statement. Okay. This is a tricky question. Please listen to this before you answer it. What do you think the highest entropy is? Let's say if I'm doing it for K classes. So imagine K is 3. Okay. So you have 3 classes, let's say triangles, X's and squares. Okay. In what case you will have the, you can say maximum uncertainty?
Then probability of each is 1/3.
Absolutely right. When I say that M is equal to N equal to P,
Yes.
okay. Okay, so if you substitute it in this equation, can I say that I will get minus 3 into 1 by 3 log of 2 of 1 by 3? So you will be writing minus 1 by 3 log 1 by 3 three times, right? If you compute Shannon's entropy, you'll be writing it like this, right? Minus 1 by 3 log 1 by 3 basis 2. For each class you will write, right? If you're computing the Shannon's entropy, yes or no? There are three classes. So I can write it like this, 3 and 3 get cancelled out, minus log 2 of 1 by 3. Okay, and I can write this as log 2 of 3 to the power minus 1. So this is log 2 of 3. Do you realize something? This is not 1, it is actually higher than 1. See, I can write log 2, 3 as log 2 of 2 to the power 1 point something, right? Yes or no? It is greater than 1. Okay. So the value that will come out, okay, is going to be greater than 1 for sure. Okay. So for K classes, what is the exact number?
Log of the number of classes.
Log of the number of classes. Okay. Please keep this in mind. Don't answer 1. Okay. The range of entropy is not between 0 to 1. It is between 0 to log 2 of K. Does that make sense?
Yes.
Okay. All right. Keep that in mind. So the range of entropy is, many people answer directly as 1, okay, which is not correct. Okay. So we have just seen, okay, how to compute this entropy. Okay. So I have a simple question. Okay, let's see this. So if I give you this scenario, what do you think the entropy would be? There are 10 x's and 10 triangles. You can directly compute it. You don't even have to see. Entropy would be 1. You just computed it, right?
1 second.
Entropy is 1. Okay. Does that make sense? Okay. And what do you think the entropy of a pure partition will be?
0.
So can I say that I can determine on the basis of entropy that I will not go further if entropy is 0?
Yes.
Okay. So a very generic statement. Okay. Now let's see, how do we choose the features based on this entropy? So I am given these features x1, x2 up to xt. Okay. I have to decide which feature to choose at this root node. And my output values are, say, 10 x's and 10 triangles. So I just computed the entropy here is 1. Okay. The entropy here is 1. Okay. So I have to select one of the features, right? So I'm going to describe a process right now, how the feature is selected. Okay. So please listen to this carefully. This is the crux of this algorithm. So I have B choices to make. Okay. So if you think about a feature, what are the types of features? In general, what are the different types of features? In English, let's say. Do you remember we had this discussion about, say, probably categorical features and real features?
Yes.
Or numeric features? And categorical features are of two types, ordinal and nominal. Did we have this discussion, or you had this discussion with somebody else?
Somebody else.
Okay, so you remember it, right? Okay. So ordinal, okay. So look at the categorical feature, okay? So imagine you are trying to figure out, okay, maybe say the score of an individual based on in a test, okay? So you have the grade of that individual, okay, in that particular course. So grades typically are of the form A, B, C, D, E, F, right? And there is an ordering between these values, A, B, C, D, E, F. A is greater than B, B is greater than C, and so on. So what type of feature it is? Is it categorical? Is the feature grade categorical?
Yes.
And there is a relationship between these values, right? A, B, C, D, E, F. So that is called as an ordinal feature, where the features have a relationship between them. The values of the features have relationships between them. Another categorical feature is like, I'll give you an example. For example, think about day of the week. Can you say Sunday is better than Monday?
No.
No, right? So it's a categorical feature, but you cannot compare these values. That is called as a nominal feature. So is the differentiation between categorical features clear? So ordinal features are those where you have an ordering in the values. There are relationships between the values. You can compare them. In nominal, you cannot. No ordering. Okay. And numeric features are straightforward. They are real values, right? Okay. So I'm going to talk about how do you create a split. Okay. So let's say I use a categorical feature here. Okay. I have 10 x's and 10 triangles. I'm going to use some categorical feature. So let's say I'm going to use the feature grade. Okay, so I have this column called as grade. I have so many other features. Okay, but there is a feature called as grade. Okay, and the output values are like some are x's, some are triangles. Okay, I'm going to use this feature to split. Assume I'm going to use this feature to split. So there are some values which are a's. There are some values which are b's. Assume that I have only 3 values, A, B, and C. So grade has only 3 unique values, A, B, and C. So when I'm going to split this node based on the feature grade, can you tell me how many children should I create? How many partitions are possible based on grade? If there are 3 unique values in grade.
3 partitions.
3 partitions. So you will put all the values of A in one partition, all the values of B in one partition, and all the values of C in another partition. Does this make sense to everyone? So depending on how many categories are there, you will create those many splits. Is that part clear? Yes, people. Okay, great. I know this is becoming complicated, but try to follow. Okay. It stays the same for nominal features also. If you have 7 days in a week, okay, so if you use the day of the week as your split criteria, then you will create 7 children. Okay, keep that in mind. Now let's talk about a numeric feature. This is where things get interesting. Okay. So, okay, let's try to understand this first. So let's say for those values which are A's, I may get say 5 x's here and maybe say 2 triangles. Maybe I see 5 x's here and I see the remaining 8 triangles go here. Okay, so do you see that? Did I cover all the triangles and x's completely?
Yes.
Okay, I mean, so the idea is you are going to use these values to put the values of y in the correct partitions. Okay. All right, let's think about a numeric feature. So imagine there is a numeric feature. Let's call this numeric feature as, so maybe this is one of the features. Let's call this feature as xi. Okay. And this has some values, maybe say 10, 20, maybe 30, 40, 50, and 60. So these are the values. Okay. Let's try to understand how to split a numeric feature. So one of the ideas to split a numeric feature is this. So if I am here where I have 10 x's and 10 triangles, I'm going to use this feature xi. So how many children should I create if I'm going to use a threshold?
So 2.
2 only, right? It's only going to be a binary split. Okay. Now let's decide how to use this threshold. What thresholds do you think are possible?
Should I take the mean of it?
That is one way to do it. Okay. Any other things? Can you take the median also?
Yes.
Any other thing? Can't you use the sample values themselves? Yes or no? I can use these thresholds. Let's say I use the sample threshold as 10. So only one of the samples is going here. Towards the left of it, only this sample will go here, and all the other 5 will go here, right?
Yes.
Okay, I can use that also. So sample values can also be used. Does this make sense? Okay. Is this clear or not? So for a numeric feature, you can use any of these values, right? Okay. I'm going to talk about which one to use effectively. Let's wait for that. Okay. So now you have understood, okay, if a categorical feature is there, what are the splits? If your numeric feature is there, what are the splits possible? Okay. Let's see how to decide on what feature should be selected. Okay. Now, I'm going to give you a small analogy to understand this. So this is the situation where I'm at. Okay. So imagine I'm going to show you with the two splits only. Okay. There are two scenarios. So I'm using a certain feature xi here, and this is certain feature xj. Okay. Certain feature xj. I'm going to split based on xi and xj, and then we will see, okay, which one is better. So if you look at this feature, let's say the threshold is maybe say 10. So maybe say 8 triangles come here, and say, so 2 triangles will go here. Okay. And let's say all the 10 x's come here. So this is how the splits look like. Okay. This is one scenario. And the other is that this is all 10x and this is all 10 triangles. Which one is better, do you think, in your opinion?
XJ.
XJ, right? So we got pure partitions here. So can I say that if I were to look at a feature which is going to be used for splitting, I will prefer that one which gives me the most pure partitions. I think we have discussed this already. And I'm going to show you a method how to measure it. So we have to give a mathematical quantity for this. So can I say that with respect to the parent, if I'm able to minimize, okay, what should I do to get pure partitions? Minimize the entropy or maximize the entropy?
Maximize the entropy.
Think about this again. And there are only 50-50 chance.
When we are certain the entropy is 1, right?
No. When do you see? You said this is better, right? What was the entropy at this stage?
At this state, it's both are equal.
1. Okay. That is the entropy at this stage.
0.
0. So you yourself said that I want to end up in pure partitions. So if you want to end up in pure partitions, what did you see? What was the resultant entropy? Did it increase or decrease?
Decrease.
So your objective should be to minimize the entropy in the children. Okay. So the way to measure it is this. Okay. So what we say is that I'm going to select that particular feature which minimizes the entropy the most. So I am going to effectively measure how much the entropy was reduced. So I'm going to measure reduction in entropy. So can I say that the reduction in entropy would be nothing but entropy of the parent minus, let's say, the entropy sum of the children? Yes or no? This much the entropy would have reduced, right? Yes or no? This much the entropy would have reduced?
Yes.
Okay. It is not exactly the entropy sum. This is called as weighted entropy sum. Okay. I'll explain what the weight is here. Okay. In just a moment. So what you are seeing is I will compute this value for every feature. So I will compute this for x1. I'll compute it for x2. I'll compute it for xd. I'll use it for all the features. And whichever feature, now tell me this, whichever feature maximizes this or minimizes this, I'm going to use that. Whichever feature maximizes this or minimizes this, I'm going to use that. Think about it. You're measuring the reduction in entropy, how much the entropy has been reduced. So which feature will you pick? The one which reduces the entropy the most or the one which I mean, gives you the maximum entropy in your children,
Reduces the entropy.
right? So our objective is to maximize this, right? Reduction in entropy. Does that make sense?
Yes.
Higher the better, right? Okay. I'm going to give you some more details. So some people, okay, let me ask you this. Do you realize that when I'm trying to measure it for X1, and let's say I'm trying to measure it for X2, entropy of the parent is not going to change.
Yes.
The parent will be the same for both, right? So can I say that what is it that I'm trying to do with this? Only focus on this term, forget the minus part. What is it that I'm going to do with this sum, weighted entropy sum? For the best feature, what will this value be?
For the best, it would be 0.
So which means that you have reduced all the entropy in your parent. Okay. So you want to minimize this value, right? Yes or no? The best feature would minimize this, right? Because entropy of a parent would be the same for everyone, right? Yes or no? Does this make sense? Because this subtraction has to be the maximum. When it would become maximum, when this value is 0. Okay. So let's try to understand with this small example how to compute this. Let's try to find the reduction in entropy for Xi. Let's try to do it for this Xi. Okay. So what is the entropy of the parent? 1. Entropy of the parent is 1. This is 1 right now. You are going to compute the weighted entropy sum. So entropy of, let's call this as child 1 and child 2. What is entropy of child 1? You can compute this directly.
0.
0. Entropy of child 2 we can compute, right? So this would be minus 8 by 18 log 8 by 18 minus 10 by 18 log 10 by 18. Yes or no?
Yes.
This is your entropy of child 2. Okay. Okay, let's try to understand what is weight here. I told it's weighted entropy, right? Okay. So when you look at the splits that you created, can you tell me towards the left-hand side, how many samples came?
2.
2, right? So out of the 20 samples, 2 samples came to the left, and that is the weight of your child 1. Okay, so you multiply this number. So weight of child 1 is nothing but the proportion of samples that came to this child. Okay. Similarly, what is the proportion for the second one?
8 out of 10 plus 10 out of 10.
Basically 18 out of 20. No, you're not going to count it separately. You are looking at the samples right now. Okay. So weight of child 2 is going to be 18 out of 20. Okay. I mean 18 by 20 essentially. So you know entropy of child 2, you know this. Okay. Entropy is always positive. Please remember this, entropy cannot be negative. I told you the range of entropy is what? 0 to
Log
of number of classes. Okay. Number of classes will always be what? Greater than?
of 0.
Equal,
Greater than equal to 1.
greater than 1, not equal to 1, greater than 1.
Yeah, 2.
Or greater than equal to 2. Okay. All right. So that value will always be greater than equal to 1. Okay. The highest value. Okay. So this is the entropy that you compute for Xi. Okay. Let's compute the reduction for Xj. So this is not going to change. Entropy of parent is going to still be 1. Okay. Let's see the child 1 here. This is child 1, this is child 2. I've already computed the entropies of child 1 and child 2, which is 0, by the way. So this is how many samples are going to the left? 10, right? So this is also 10 by 20. So this is 10 by 20 multiplied by 0 plus 10 by 20 multiplied by 0. Do you see that? The entropies, because they are 0, this sum is 0. Yes or no?
Yes.
So if this is 0, what is the reduction? This value. You have reduced all the entropy. So which value do you think will be higher? This or this? Which value will be higher, the bottom one or the above one? This is always positive, okay? Please remember. This is always positive. This weighted sum will always be positive. Entropies cannot be negative. So which would be higher? Reduction in entropy for xi or reduction in entropy for xj?
XJ.
This would be higher. This is higher. So if you are comparing these two, you will pick xj. Okay. So what you do is you repeat this process for all the features. Okay, you repeat this process for all the features. Okay. Now, what type of thresholds can you choose? Mean, median, and sample values. So for a numeric feature, you have to use it for all the thresholds. Okay. For a numeric feature, you have to use for all the sample values. This is what is actually used. Okay. So when you are thinking of splitting with a numeric feature, you will first try all the sample values. And then you will see which sample value is giving you the best result. Okay. You repeat it for every feature. So which feature would be picked at the end? One that minimizes the entropy the most. That gives you the highest reduction in entropy. So is this part clear? Yes or no?
Yes.
Okay. Please note this. Entropy, this reduction in entropy is also called as information gain. So you want to maximize the information gain. Okay. So you actually select that particular feature. So select that feature which maximizes the information gain. Okay, for your candidate split. Do you want me to do it on a small data set? A real data set? Do you want me to do it? Or is the process clear to everyone? So you keep on recursively doing it until you get only pure nodes. Do you want me to show on a real data set?
We can do that, like implementation part you'll be doing, or
No, implementation will be doing it, but do you want me to show all the values, solutions and everything on a small data set?
in implementation we can cover that.
No, in implementation it will become hard. Because I mean, like, if I were to use 5 samples, right, I would have to show you the tree and everything, right? Okay, I'll do that in the implementation also. Okay,
We can see one sentence so that,
that's the question.
yeah, we can see.
Okay, let's see this. Now we'll do it in the implementation also, don't worry. Just a second. Okay, let's say this is the data set that we have. Just give me a second, okay? I'll just clear some of the things. Okay, so look at this data set. So there are around 14 samples. So if you look at these, this particular example, this is nothing but the index only. There are 14 samples. Okay. The objective of this data set is, I mean, you have to decide if a person is going to buy a computer or not. This is the output. This is your output Y. So by looking at this output, can you tell me what type of task it is?
Binary.
Binary classification. It's binary classification. And these are your 4 features. Based on these 4 features, you have to determine if somebody is going to buy a computer or not. So age, income, student, and credit rating, you have to determine if a person is going to buy a computer or not. Okay. Let's start building our tree. Okay. So this is the data that you have. So if you count, okay, there are 9 yeses and 5 nos. Okay, so what is the entropy of the parent? What is the entropy of the root? Minus 9 by 14 log of 2 of 9 by 14 minus 5 by 14 log of 5 by 14. Is this part clear to everyone?
Yes.
Yeah. Okay. All right. This is the entropy of our root node. I have to minimize it now. So how many features are there? Look at this data set again.
4.
4. So out of the 4 features, you have to decide which one to choose. So let's start by picking them one by one. Okay, and then we will see, okay, which one is better. Let's try to use age first. So if you use this feature age, how many splits will I make?
3.
3. Can I say that it's a categorical feature?
Yes.
Okay. So you will be making 3 splits. Less than equal to 30, 31 to 40, and greater than 40. These are your splits, by the way. Okay. So I'll show you, okay, this is how the splits are made. This is what you get. So using this feature age, this is what you get. Okay. So out of the 14 samples, okay, out of the 14 samples, these are the 14 samples. Green actually means a yes and red means a no. Okay. So out of the 14 samples, you can see that 5 are going to the left. You can look at it from this data that this has been sorted for you. Okay. So from these 5, can you see that there are 3 no's and 2 yeses?
Yes.
Okay. Similarly, for 31 to 40, you actually see it here. All of them are yeses. And for greater than 40, it's shown to you here. Okay. Now, I have a question for everyone. What is the, can we compute the entropy of the children? We can, right?
Yes.
So, what is the entropy of the middle one? You should be able to compute it directly without even doing anything.
0.
Okay, pure 0. This is a pure partition. Okay, entropy will come out to be 0. Okay, look at this child 1. So entropy of this would be minus 3 by 5 log 3 by 5 minus 2 by 5 log 2 by 5. Do you agree?
Yes.
Okay. Do you see that it is the same for this also? It's just that the roles have been flipped.
Yes.
The classes have been flipped. Okay. It's the same for child 3 also. It's just that yes has become no, no has become yes. Okay. But it stays the same. Entropy is the same. Okay. Now, how do I compute information gain for X1, this feature age? Look at the entropy of the parent, which you computed earlier.
Minus this sum of the
Minus 5 by 14. This is what we computed, right? This value. Yes or no?
Yes.
Okay. And what is the weighted entropy sum of the children? So this would be, what is the weight of child 1?
5 out of 14.
5 out of 14. You have computed entropy of child 1, which is this. Okay. 4 out of 14 into entropy of child 2. What is entropy of child 2?
0.
So this is not going to contribute. And similarly, 5 by 14 into entropy of child 3, which is entropy of child 1 again.
Yes.
The same. Okay. Entropy of child 1 and entropy of child 3 are the same. Okay. So you can compute this value, right? Can I say that that would be information gain for age?
Yes.
Okay. All right. Now, I'll just repeat this one more time. Let's say if you were to use student, how many children will you create?
2.
2, right? Okay. If
Yeah.
it's a student or not. Okay. So I've done all the calculations in one slide. Look at this. Okay. I wanted to focus on this. Okay. Just give me a second. Okay. I'll wrap everything. Okay. See to this carefully. So for age, we saw that there are 3 children, right, that we came up with. Can you see that entropy of child 1 and entropy of child 3 is the same?
Yeah.
Okay. The entropy of parent is this much. And if you compute information gain, this will come out this much, 0.2467. Okay. If you were to do it for student, you said that you will create 2 children, right?
Yes.
So these are the values for it. These are the values for it. If you do it for student. Okay. All right. Same thing I've done for the other 2 as well. This is for income. Okay. The income is on the, on
Three
which
categories.
in the highlighted region now. And this will be for your credit rating. Okay. Now I have a question, okay? Which one should I select? Which is the better one? Should I pick the one which has the highest information gain or the lowest one?
Highest information gain.
So figure out, okay, which one is the highest by looking at the slide.
Age.
Age. I was highlighted also in your orange color. Okay.
Mhm.
This is the tree so far. Okay. 1 second. I'll just rub this. Okay. I actually use this slides, okay, to teach to all my students. So that's why there is a lot of clutter right now. Okay. So this is the tree right now. Okay. My next question is this. Is there a need to split the middle child?
No.
No, right? Because entropy is 0. So there is no need to split it. Can I say it becomes a leaf node?
Yes.
Yeah.
Okay. All right. Great. Okay. You have understood the process. Now let's talk about this. Child 1.
Hmm.
How many samples are there in child 1?
5.
5. Okay. See to the right hand side of this slide. Okay. To the right of this slide. The 5 samples that I am depicting are these 5 samples, by the way.
Hmm.
All of these values are actually having the age as less than 30.
Yes.
Is that clear? These are those samples whose ages were less than 30. Okay. So they came to this left hand side. Now I have a simple question for everyone. So if you are on this side, do you think you can reuse the feature age again?
No.
Right?
If I'm on one particular class already less than 30, now
Oh,
all
that's right.
samples are in the same.
Class, right? So that is why, do you see that I have not highlighted age in this table that you see on the right?
Yes.
Okay. So can I say that if you have used a categorical feature, you cannot reuse it again?
Yes.
But a numeric feature can be used any number of times.
Yes.
Okay. Keep that in mind. Okay. That's also an interview question. Okay.
Sanatan, can you repeat it once? I don't get it actually.
Okay. So how many features that you have? Think about it.
I have
Four.
4 features. Yeah.
Okay, so you are going to decide which feature to use to split it. Okay, for this node, you have to decide it, right? Do you realize that you have to split it because entropy is not 0?
Yes.
So I have to decide on what feature should I split. The first question was, can I use the feature age? That's the question.
To split.
Okay, if you were to use the feature age, look at the data that you have. How many children will you create? Okay, what are the respective values of all the ages? If you come to this left hand side, what are the values for it? Age
For
is
the age.
Same.
less than 30, right?
Yes.
So do you think that can you create more age categories in it?
No.
Because there is nothing which is between 31 to 40,
Yes.
greater than 40, right? So if I have used this feature age, okay, do you think I can reuse it? That's the question. Don't use, I mean, wouldn't you feel that it's the same partition again? I cannot even reuse it.
Yes, because I've already used the 30.
You have already used it 30, right? I mean, if you want to create it, let's say you create 3 children like the way you originally created. Okay. So less than 30. So all of the values will go here, right?
Yes.
Does it make sense to do this?
No. Okay.
Between
No.
31 to 40, there would be nothing, right? Between greater than 40 would be
40.
nothing.
Yes.
Okay. So you don't have to do this, right? Because it's already done for you.
Yes.
Okay. So I'm saying that if you have used a categorical feature, you should not reuse it. Okay. It doesn't make sense at all. So that is why, I mean, in the table I was saying, you don't even see age, right? I mean, I created it right now for you guys just to understand this. Okay. All right. So what are the possible options for me that I need to check?
Income, student, and credit rating.
Income, student, and credit rating. Okay. I'm going to ask you one simple question. Just by looking at it, you can tell me which feature should be used. You don't even have to compute anything. You can actually see there is a clear relationship. Which feature should be used?
Student.
Student. Spot on. You see that, okay? If the student is a no, what is the answer?
No.
No one buys computer, right? 3 no's for the computers. Okay. This is for the computer. Okay. Bias computer. Here student means a no. Okay. And if the student is a yes, you have 2 yeses. So you have reduced all the entropy. Do you see that? You become both the nodes become terminal nodes, right? Leaf nodes. You don't even have to compute anything. You just have to check. Just by looking at it. You can compute it. You will see that student will have the highest information gain. Okay. So would I split these children further? No, right? The entropy is 0. There is no need to split them further. So can you repeat the process for this?
Yes.
You can, right? Okay. So you have to keep on doing it till all the nodes become pure. So you are recursively partitioning your data till all the leaves become pure. So is the algorithm clear?
So in this
Yes.
case, for calculate, when I do the second split based on student category,
Mhm.
information gain will be calculated with taking that
Which is
than
7-1.
okay, this would be my parent entropy.
Should be the parent in that case, right? Because it is coming from those 5 samples.
Okay.
Make sense?
So information gain is like level by level. Like when I do the
Yes, level by level.
category, one information
It
gain
is from the parent, the direct parent, not the grandparents or great grandparents. No.
Okay.
From the direct parent only. Anything else? So the algorithm clear, right? I hope we have seen enough examples just to get the hang of it. Okay. This algorithm is called as ID3, which recursively partitions your data using the criterion called as entropy. Okay. You're using this criterion of entropy to decide like what to, when to split and when not to split. Okay. You're trying to reduce the entropy with information gain. Okay. ID3 stands for iterative dichotomizer version 3. Just a very fancy name. Version 3. Okay. Now I'm going to show you some other metrics which can be used. Okay. By the way, this is the complete tree. If you want to see, this is the complete tree. So for the given data, for this given sample, can you tell me what would you predict? For the given sample, can you tell me what would you predict? If the person will buy a computer or not?
yes,
In which node do you end up?
the second one, the like
Second. Okay. So you directly see, you go to this, okay. You see that, okay, age is being compared. So you come to this and you directly get your answer. Okay. All right. So that person the person buys a computer. Okay. All right. Okay.
Sir, with the file you're gonna upload, do you
Yeah,
upload this PDF?
yeah.
Yeah, thank you.
I've been doing it for, for the previous algorithm.
Yeah,
so-
yeah, I've seen it, but I'm just
So
asking.
one more question over here. Suppose I have reached the node, the first. Can you please scroll back to that decision tree? Okay. First, I use age as my feature to decide.
Yeah.
Then for the first section of age, that is less than 30, I use one feature to split, and I can use some other feature to split in the other category. Like for age greater than 40, I'm using some other feature, not the student one to split.
Correct.
So it will be
For greater than 40, right? There will be different 5 samples. Do you remember?
yes.
For these 5 samples, credit rating was better.
Okay.
So here we came up with student as the best feature for splitting, right? On the left hand side. But on the right hand side, it will come out to be credit rating. You can compute it. Okay. I don't have the results right now. But if you just go through it, you'll be able to figure out what 5 samples are there. And if you see credit rating, directly divides it. Okay. Is this clear?
Yes.
Okay. All right. Okay. All right. So the decision tree is done. Okay. Let's see some more criterions just to understand. Okay. What other things that you will see in the implementation. So one of the criterions, which is an alternate to entropy, just a second, please. So one of the criterions, which is alternate to entropy, is called as Gini impurity or Gini index. So this also measures the idea in the same way. It is a measure of impurity only. See, if you think about Shannon's entropy, right, that is a measure of uncertainty, impurity. Okay, it's the inverse of purity, so it's impurity only. Okay. Now, how does it measure it? It's actually very simple. So the formula for this is 1 minus summation of I equals to 1 to C, the probability of all classes squared, and then you are summing it up. Okay, this is your Gini. This is your Gini impurity. Now let's try to understand this. Okay, so this also measures uncertainty. This also measures the inverse of purity. Okay, so I give you this box M, X's, and triangles. Can you tell me when there would be maximum purity? When there would be maximum purity? We have just done this.
If any one of the
0, right?
sample was 0, yeah.
So which one do you want me to assume as 0?
Let's assume n as 0.
Okay, let's say n as 0. So probability of X is a 1 and probability of triangle is a 0.
0, yeah.
Okay, makes sense. Put it in the formula. Look at this value. It is 1 minus, what is probability of X squared plus probability of triangle squared?
1.
0 squared, 1 squared plus 0 squared. What is this value now?
0.
0.
Any impurity?
No.
No.
All right. So it's the same thing doing its job as entropy. Okay. But the highest value will be different. Okay. So when there will be maximum, say, impurity, what should be the relationship between M and N?
Equal.
Equal. So probability of X is half, and which is equal to the probability of triangle also. So if you put it now, what is the formula?
Square plus.
Does this make sense? 1 by 2 squared will be 1 by 4. Again, the different 1 by 2 squared will be 1 by 4. If you add them up, you'll get 1 by 2. So 1 minus 1 by 2 is going to be 0.5. So this is the maximum Gini. Now, if I ask you, what should be the maximum Gini impurity for K classes? What should be the maximum Gini impurity for K classes?
For example, it's 1 by 3. So 1 by 3 square plus 1 by 3 square plus 1 by 3 square.
That will be into 1 by 3 square. Cancel out 1, 3.
8, 8 by 9. So it will be.
Okay, let's try to simplify it. Okay, that will be 1 minus 1 by K. Yes or no? Makes sense?
Okay.
1 minus 1 by K. Okay,
Yeah.
so you can compute it like that. Okay, I hope it's well understood. Is it clear?
Yeah, yeah.
The maximum value would be 1 minus 1 by K. Okay, all right.
1 minus 1 by K or 1 minus 1 by K square?
1 minus 1 by K. This is nothing but, see, you are 1 minus, you are summing up these 1 by K square, right? Yes or no?
K by K square, so it will quickly cancels. Okay.
Make sense?
Yes.
All right. Okay, so this is the range for your Gini. I'm going to tell you one more, but that is a little intricate, so do try to follow. This is the same. It measures the impurity in its own way, but it's slightly different. Okay, you have actually seen this before, but in a different context. So this is also called as log loss. Where did we see it?
Logarithmic regression.
Logistic regression, not logarithmic, logistic. Okay. Okay. So, but this is the probabilistic log loss. Okay, let's see how. So this is probability of a class I log of, so this is, let's say, actual value of I should say. Probability of actual value of a I okay, log of probability of yi hat, and you're going to sum it up for C classes. Okay, I'll describe what this means. Okay, I'll describe what this means. It's a little intricate. Okay, to understand this, let's take a small illustration. Imagine that I have 10 x's and say 20 triangles. Okay, or rather, let me take 10 x's and 10 triangles. Okay, so my y values is some of them are x's, some of them are triangles. Okay, so if you are in this node, okay, maybe I'll just change it slightly so that you understand it. Okay, let's say this is the situation. So what will you predict for class X and class triangle? So if a sample is used at this node, what would you predict?
Triangle.
A triangle.
Right, but what is the probability for it?
20 out.
Y hat probability, okay, because you're using it for predictions. What is the probability for say class X?
Class
And-
X would be 1/3 and that triangle would be 2/3.
Makes sense, right? Okay. So the actual probability is this. Okay. So I have 10 x's and 20 triangles here. Okay. I'm going to make it like this. Okay. Please see to this very carefully. So I'm going to one hot encode it. Okay. So I have two possibilities, right? X and triangles. Okay. So imagine that my first sample was actually an X. My first sample was actually an X. So which value would be 1 if you one hot encode it?
X value.
X value, and this would be 0, right? So can I say this is the probability of the actual values? Does that make sense? This is the probability of actual values, right? Okay, let's try to do this. Okay, so if you look at the first sample, okay, if you look at the first sample, can you put it in the formula? What would be the answer? Look, do it for the first sample, okay? Do it for the first sample. So what is the probability of the actual sample for class X? Probability of X, okay, this is the actual value. Log of probability of the predicted value. Okay, this is the predicted value. Okay. So what is the probability of the actual value?
1
1. This value is 1. What is the probability of the predicted value?
by 3.
1/3. Okay. Can you repeat it for the next class? What is the probability of the actual value for triangle?
0.
This is 0. So do you think this second value contributes anything?
No.
No.
No, right? So do you realize that, okay, the second value, because ultimately whichever class it is, right, that should play a role. This thing goes away. Okay. All right. I hope this makes sense. Okay. So this is for one sample. Okay. How many samples will actually be X in this Y? How many samples will actually be X in the output Y? 10, right? Okay. So can I simply multiply this number by 10?
Yes.
This will be just added up for all the 10 samples, right? Okay. And how many of them will be triangles?
20.
20. And what, so can I put it like this? Minus 20 times, what is the actual probability of triangle? That will be 1, right? For those. And log of probability of triangle would be 2/3. Okay. Does that make sense? Yes or no? Does this make sense?
Yes.
Okay. So what is the actual answer for you? What is the actual answer? So this is okay. See, please note this. So this is minus of 10 times log of probability of 1/3 minus 20 times log of probability of 2/3. This is your answer. This is the log loss. Is this clear? Okay. All right. So this is for this. Okay. If you compute this, this will come out a very positive value, highly positive value. Okay. It will be between 0 to 1 only. Okay. No, not 0 to 1. Sorry. I mean, currently this can go up to infinity, positive infinity, 0 to infinity. Okay. It depends on how many samples are there essentially. Now I have a simple question. Please listen to this very carefully. in what case I will not have any what we say is impurity. When one of them is 0, right?
Yes.
Okay, so if one of them is 0, which do you want me to make as 0, 10 or 20?
Then triangle to be 0.
Okay, let's assume this number 20 becomes 0. So do you think that this will go away?
Yes.
Yes.
20 has become 0, right? Okay. What will be this probability if 10 is only present? This will be 1, this will be 0.
Yes, 1.
Okay. And what is log 1 by 3? In this case, that will be replaced with log 1, right? What is log 1? 0. This will also go away. And that is what you want, right?
No loss.
No loss. So do you realize this also works in the same way?
Yes.
Give you an analogy, okay? All the metrics that I have described, they measure uncertainty. They measure impurity. So if there is no impurity, they'll give you a 0. If there is impurity, there will be a positive value for it. The ranges would be different. Okay. So here for this, it would be 0 to infinity. Does this make sense?
Yes.
Okay. So this also measures it in the same way. Okay. But the formula is subtle and slightly different. So you will see all these criterions in your implementation. Okay. Let's try to understand some more concepts. Let's see how to use it for regression. Okay. So the idea is the same. I have the features and this output y, but the output here is now real. It's a continuous output. Okay, I'm going to show you a small illustration just to show you this. So imagine this is my output 10, 20, 30, 40, 50. Okay. I mean, this is my output, okay, 10, 20, 30, 40. So I have 4 samples essentially, and all these 4 samples are lying here. I have a simple question for you guys. Okay, please see to this very carefully. You can maybe note it down as say y1, y2, y3, y4. Yeah, you can imagine it like this. Don't even forget about the numbers. Just imagine it like 4 values. Okay. I have a question. So in classification, your objective was to create pure partitions, right? Yes or no?
Yes.
Okay. So here the objective is slightly different, but the idea is very, very similar. So again, you will try out all the features. First, you will try x1, you will try x2, you will try up to xd. Okay. Now we have to discuss, okay, how to decide, okay, which feature to choose. Okay. Let's say I'm using one of the features. Let's call it some feature xi. And I'm going to use a certain threshold. So do you know how to split? Like if it's a categorical feature, how many children will I make?
2.
No, if it's a categorical feature. It depends on the number of categories, right?
Yes.
Okay. But if it's a real feature, I will create 2 children, right? So I'm going to create 2 children. Let's see to this. Just imagine I'm going to create 2 children. Okay. Threshold, you know, right? You can pick different thresholds. Okay. My question is this. When you are creating, so instead of remembering these values as 10, 20, 30, 40, you imagine these values to be real values. Okay. Please remember they are real values now. Okay, they are real values. They are real values. Don't remember them as 10, 20, 30, 40. Okay. So if I use a certain real feature to split the data, so some of the values will probably go here, maybe say y1, y3, some of the values will go here. Yes or no? This is what a split would do. Some features will be sent to the right, some values will be sent to the left. Okay. I have a simple question for you guys. Please try to understand this. When you're trying to make a prediction, okay, first of all, your prediction, so in classification, what was your objective? Whether y2, y4 should be the same or y2, y4 were different when you are trying to create a partition? In
Same.
class, they should be the same, right? That's why you wanted pure partitions. Here we don't have, I'm not saying that I have categorical values. So I have real values. So the question is, do you want them to be close by or do you want them to be far away? That's the question. Do you want them to be close by or do you want them to be far away from each other? Think about this. Okay, let me ask you this. Okay.
Far away.
That's wait, okay. I'll describe why. It's wrong. It's the other way around. 50-50 chance, okay, you have failed. Okay, look at this. So imagine that this is the data that I give you. Okay. So these are real values. Okay. This is say one feature. Okay, and this is the output y. Okay, I'm giving you real values just to demonstrate something. When you say the values are far away, would you create such a partition? Or would you create these three partitions using these thresholds?
Vertical ones.
But these values are close by now.
Yes.
You understand it why we created close by partitions, right? Because when I'm going to make a strong prediction, it should come from close by samples. It should not come from far away samples, right? Yes or no?
Yes.
Concept in classification. All the samples have to be the same. So since our values cannot be the same, but they can be close by, right?
Yes.
No, okay. So I'm going to create these partitions such that these values are close by. How do I measure if the values are close by? So if I give you a set of values, let's say A1, A2, A3, A4. Do you want me to give real values or is this fine?
This is fine.
Okay. So how do you measure the spread of the values?
Difference.
One way is to measure the difference, but there is a metric that you guys use very frequently. Okay, let me give you these values, okay, and tell me how much is the spread. All the values are 1. What is the spread?
0.
0, right? Okay, so how did you compute it?
No difference in the values.
No, see, how many computations are you doing? I want to know that.
Okay, so it's like deviation on variance that we use.
Yes. Variance gives you a measure to do it, right? In variance, what do? You find the mean.
Mean and divided.
The difference of the mean from every value, you square it up, and then you take the average, right?
Yes.
Okay. That also is one way to measure, right? Another simple way to measure is, I have these 4 values, right? Do you think I can count the distances of the 4 values? Yes or no?
Yes.
I have 4 values. How many pairs can I make?
4 choose 2.
4 choose 2. So basically, do the summation of the 4 choose 2 combinations. So these are the 4 choose 2 combinations, 6 combinations. Do you see that if I can measure it, it will tell me how much the spread is?
Yes.
If you look at this, what is the spread? Zeros, right? 0 plus 0 plus 0 plus 0 plus 0 plus 0. Yes or no?
Yeah.
Okay. So you can use the variance also to measure the spread. You can use this absolute error also to measure the spread. Do you think I can square these values and still measure the spread?
Yes.
This is called a squared error. Okay. Okay. This is called a squared error. You can still use it. Okay. A variant of this is called as Friedman MSC. Okay. Friedman mean spread error. If you're interested, you can read about it. So you will see these options in your criterions. So when you are trying to create a regression tree, what is the objective? To minimize the variance or maximize the variance? The feature that minimizes the variance the most or maximizes the variance?
Minimize.
Minimizes that. Okay. So you are going to use that particular feature. So you will see these things, by the way. Spread error, absolute error, Friedman MSC. Variance, minimizing the variance is actually equivalent to this. Minimizing the variance is actually similar to minimizing the spread error. There is a proof for it. I'm not discussing the proof. It will take me another 20-30 minutes just to demonstrate this. Both are kind of equivalent. Okay. there is a relationship between minimizing the squared error and minimizing the variance. Or rather, let me write it. You try to prove it. Okay. So n square times the variance is nothing but the pairwise sum. Try to prove it. The pairwise squared sum. If you know the formula for variance, you know how to compute pairwise squared sum. Okay. So if you multiply n square with variance, you will get pairwise squared sum. Okay. It's easy to prove. It's very easy to prove. You will not get a proof, probably a derivation for this on the web. So essentially what I'm saying is, if n square is the number of samples, right, it's a constant. So minimizing variance is equivalent to minimizing the pairwise squared sum. That is what this means. So that's why I said they both are equivalent. Okay. So how do I measure? Okay, because I'm creating multiple children, right? So basically what you do is you measure the sum of the, so you're not subtracting it from the parent. Okay, you're not subtracting it from the parent now. You will simply measure the sum of variances, or say the sum of squared error across the children. Across the children. So whichever feature minimizes this, okay, whichever feature minimizes this the most, use that feature. Okay, the feature that minimizes this. There is no relationship to the parent now. Okay, you can think of sum of absolutes. So we'll simply find out, you can say squared error of this child, squared error of this child, and you will simply sum it up. So squared error of child 1 plus squared error of child 2, whichever it is the least for whichever feature, you will pick that. Okay, and you will have to see thresholds as well, because thresholds will be different also. Okay, so this is called as a decision regressor, or a regressor, decision regressor tree, if you want to call it, or decision tree regressor. Okay, so we'll see all of that in the implementation. I still have 10 minutes, so I want to discuss a few other things. Any questions before this? Yeah.
Can we see this regressor decision tree with some value examples?
No.
No.
No, I don't want to waste any more time. Okay. See, if we do this again, do you know I had only half an hour to discuss this, the whole concept. It's almost 2 hours. Okay, so I mean, please spend some time. Okay, because if I do the same thing again and again, I hope the idea is quite clear, right?
Yes, idea is clear.
So maybe I'll show you in the implementation.
Okay.
All right. So yeah, I had actually 1 hour in total to just discuss decision tree with implementation. I've already spent 2. Okay. I have to cater to everybody's learning speed, right? So I have to pick up the pace as well. Otherwise, you guys will complain later on saying that you are asking me to deliver, say, 3 extra weeks, which we don't want. Okay. All right. If you want, I'll point you to an example, or maybe say a reference where you can see. If you just Google it, right, you'll find enough material on this.
Okay.
Okay. I mean, if you are just looking for an example for that. Okay. Okay. Let's try to, recap the concept of overfitting. So as you grow the decision tree, right, it becomes prone to overfitting. Okay, it is likely to overfit. So one idea is we can reduce overfitting by reducing the size of the decision tree. Yes or no? By limiting the size? Limit the growth of the decision tree?
Yes.
Okay. So if you want to limit the growth of the decision tree, there are many different ways to do it. So I'm going to describe the different ways. So there are 2 popular ways to do it. And in each category, you will see very, very different set of algorithms, or heuristics, you can call them. So the first type of, you can say heuristics, they are called as pre-pruning heuristics. What essentially this means is that as you are growing the tree, you set some conditions. And when a condition is met, you stop. Okay. So can you tell me what condition we can make? So let's say I'm growing this tree. Okay. I want to limit the size of this tree. Can you tell me one of the conditions that I can put? So I'm
When
growing
my-
this tree. Okay. Yeah. What conditions?
So when my there is no change or major difference in my certainty, entropy.
Major change, right? So can I say that you are putting a condition that, let's say, if the minimum entropy is
Some threshold value and not
some
bigger.
threshold value, let's say if it is 0.05. So for a node, if it is so typically I stop at 0, right?
Yes.
Okay, but if it is less than 0.05, I will not split it.
Yes.
Does that make sense? Okay, can you do the same for say minimum Gini
Yes.
and minimum log loss? Okay, makes sense, right?
Yes.
Okay, one more thing. So when you look at a node, right, you have some samples in it, right? Let's say 10 samples of class X, 20 samples of class triangle. So when this becomes pure, like when all the samples,
Come to the same.
let's say when this is M and when this is N, then one of them is closer to 0, right?
Yes.
Okay. So can I put a condition on that, like the weight of a particular class?
Yes.
Like what is the weight of class X, the probability of class X, M divided by M plus N, and the triangle is N divided by M plus N. So I can put a condition on the weight. So in the case of pure, what would be these probabilities? One of them would be
0.
0, and the other one would be 1. Okay. So you can put a constraint that the minimum weight is for the minority class, you can say, okay, let's say 0.01. Okay. If it is less than this, I'm not going to split it. That way you'll be able to limit the tree. Okay. So look at this. Okay. This is actually called as a level. So this is level 0. This is level 1. This is level 2. Okay. This is also called as depth, by the way. Okay. So do you see that I can put a constraint on the depth?
Yes.
Okay. Now, as you are growing the tree, do you see that you are creating some leaf nodes? So as you go down, you will create more and more leaf nodes, right? Don't you think I can put a condition on the maximum number of leaf nodes?
Yes.
Okay. All right. A few more things. Look at a node. Let's say this is the node that I'm looking at. I want to decide whether to split this or not. One of the things that you could do is, let's look at the number of samples in this node. Let's say the number of samples are maybe say 3. Do you want to split this?
No.
Maybe, maybe not, right? So I can put this condition as min samples, right? In a leaf node. It has to be at least 3 for me to split it. Okay. You can put a condition like 5. So if it is anything less than 5, I'm not going to split it. Okay. All right. There is one more. Let's say there is a node which has 30 samples. So do you want to split it, right? Because it is greater than 5. Let's say this value is 5.
Yes.
Okay. Now, so you want to split this, okay? But the condition is this. Let's say if you use the best feature, some xj, it gives you 29 and 1. Do you think if it was worth splitting? Don't you see that you just created a new partition for one sample? What does that lead to? Overfitting. So is it desirable? No, right? It simply means that out of the 30 samples, you just use this one sample to create a new partition, and you increase the level by 1. You increase the size of the tree, right? Which would not be appropriate because the majority of the samples are here in the other class, the 29 samples. Okay. So this is called as min sample split. Upon splitting, this has to be, say, the minimum number of samples. Okay. If it is less than 2, you don't do it. Okay. So these are some of the pre-pruning characteristics. So is this clear?
Yes.
Okay. We will see all of them in the implementation. All of them are there. Okay. And then we will see post-pruning. So post-pruning is actually the reverse. See, Tree pruning is top-down strategy. So as you are growing the tree, okay, as you are growing the tree, you are putting some constraints. Post pruning says that first you grow the tree and then you do something about it. Okay, let's see. So post pruning says that, so pruning means filtering. So you are filtering after the tree is constructed. Okay, so let's say this is the structure of the tree. So one idea is this. Okay, one idea is this. So I'm going to describe some ideas. Okay, so this is the bottom up strategy, you can say. Okay, so look at the subtree at the lowest level, like this subtree. Do you think that I can actually check my test performance with and without this subtree? Yes or no?
Yeah.
So I'm essentially saying the parent is now becoming a leaf.
Yes.
So previously these were leaves, right? Previously these were leaves. I'm saying that I'm just removing this subtree and I'm checking the performance with and without this subtree. If without this subtree, the performance improves on the test set, do you think it is worth it
Yes.
to
Yes.
remove it, right? Okay. So you keep on repeating this for every subtree as you go up. So if it helps in the performance boost on the test set, you do it. This is called as subtree error pruning. This is called as subtree error pruning. Okay. I just need 2 more minutes. Okay. But this is very expensive, by the way. This is not desirable. Okay, this is not desirable at all. So there is an alternate variant of this, which is called as cost complexity pruning. This strategy does not even take into account the test set. Okay. So I'll show you how the strategy works. Okay. So what I'm going to do is, see, once I'm using this node to split the data, don't you feel that I can compute the training accuracy at this level and the training accuracy at these levels? Yes or no? Do you think that at the moment, let's say I'm sitting at this node, okay, I'm sitting at this node, as I'm creating the tree, don't you feel that at each node I can see the training accuracy as I'm going down the tree?
Yes. Yes.
I can pass the samples back again to this tree and I can figure out the train accuracy, right? What do you think the train accuracy will be as you go down? Will it increase or decrease?
Increase.
It will increase, right?
Increase.
It will go close to 1, okay, as you make the full tree. So the idea is at each node you have the training accuracy, okay? So my question is just this, okay? My question is just this. If you expand the tree, basically you partition, you can say a parent node, and there is not much change in the train accuracy, do you think it was worth it?
No.
No.
There is not much change. So can I say that you just led to overfitting?
Yes.
Because you just did a split, which did not improve your training accuracy significantly. I'm not saying maybe it was worth it. You can do the checking on the test set, right?
Yes.
Okay. But the idea here is this. See, while I'm creating the tree, don't you think I can note down the train accuracy for each node?
Yes.
For each internal node, I'm saying. Okay. So I can do that, right? So imagine that I'm actually noting down the difference. So I'm noting down the difference in the train accuracy if like with this node and without this node. But I'm looking at only train accuracy. So what do you think? The nodes for which the difference in the train accuracies is not much, do you think shall I remove them and then check?
Yes.
Okay. This is called as cost complexity pruning. It measures the difference in the train accuracies. So what it says is this, let's say so there is a parameter called as CCP alpha, cost complexity pruning alpha. So if I put it as 0.01, so you are saying that if you get a chance of 1% increase, so this is not 1%, this is 0.0001. So this is 0.01% essentially. So what you're saying is if you get an increment of 0.01% from this, from a particular subtree, okay, if the improvement is less than this value, then you discard that subtree and then check. So what you are doing is you are discarding all the subtrees where the improvement that you got was less than 0.01. So previously, if you think about this process, don't you think you will eliminate all the subtrees one by one? The previous process which I described, as you go from bottom to top.
Yeah.
You will remove the subtrees one by one, right? But don't you think it is actually even more simpler? You discard all the subtrees whose difference in the training accuracy is very, very little, less than 0.01. If it is greater than it, well and good. It gives you a good boost. If it is less than this, discard all of them in one shot. And then you check with all the subtrees removed, whose CCP alpha was less than 0.01. Okay, you check the performance of on the test set. Did it help or not? So if it helped, then the CCP alpha gave you good result. So you will try for different values of CCP alpha. Whichever CCP alpha gives you the best result, okay, that is the optimal tree that you get at the end. So higher the value of CCP alpha, can you tell me what it would lead to? If I increase this too much, which situation I'll end up in? Okay, higher the value of CCP alpha, can you tell me, will you discard more trees or will you discard less trees? Anyone? If I increase the value of CCP alpha, this threshold, will I discard more trees or less trees? Less sub trees rather.
Decrease.
It will, see, what's the definition? See, I am asking 50-50 chance, okay, and then again I get incorrect answers. Okay. Increasing the value will lead to more discarding of the trees, more discarding of the subtrees. That means the tree will become even more shorter. So you will end up in a scenario called as underfitting if you increase it too much. Basically, the depth of the decision tree would be very, very small in that case. You would have discarded most of the subtrees. Okay, so higher the CCP alpha, you can say more subtrees are discarded. Okay, the depth of the tree, the size of the tree will actually shrink more. Okay, so you have to find a good value for CCP alpha. Please don't keep it too high. Typically, the results are good between 0 means full tree, 0. You will go up to say probably say 0.05. Even you can try for say 0.1 if you want, discarding 10% of the, those subtrees which give you 10% boost. I don't recommend that. Okay. But you can go up to maybe say 0.05. That is a good threshold to search. So between 0 to 0.05, you can maybe search for say 10 values in between. And that will be a good hyperparameter search for this. Okay. But please note that these are expensive strategies in comparison to these pre-pruning strategies. Because as you are building the tree, you are deciding whether to stop or not. Post-pruning is after you have built the tree. So they are more expensive. Okay. So we'll see all of that in the implementation in the next class, which is probably on Monday.
Sure,
Any other questions? Yes. Now we can discuss if you have any questions. Go ahead. Anyone with any questions? Yeah, anyone with any questions? I think my iPad is full. I have to delete some files. Anyways, okay, if there are no questions, I'll upload the handwritten notes as well as the slides on your shared drive folder. And you can download it maybe in the next 10 minutes. Okay, I'll stop now. So bye everyone. I'll meet tomorrow. On next Monday. Bye. Enjoy your weekend. Yeah.
Thank you.
Bye everyone.